Hello everyone, my name is Muhammet Kırık, and in this video I will be introducing a novel physical layer security application of the orthogonal frequency division multiplexing with subcarrier number modulation for the future 6G and beyond wireless networks. So let me start with what is the orthogonal frequency division multiplexing with subcarrier number modulation first. Shortly we are calling it as OFDM-SNM, and it is a recently proposed technique that aims to convey additional data bits by exploiting the number of active subcarriers. So we are not satisfied with this scheme because even though the proposed technique of OFDM-SNM creates so many advantages such as the low bit error rate, high spectral efficiency and high reliability, it still suffers from the security vulnerabilities against the eavesdropper and malicious wiretappers. So in order to eliminate these security vulnerabilities, we are proposing the system model that we are introducing here in the figure 1. So let me go through this figure one by one to give you a better understanding. Firstly, let's just imagine that we have incoming bits and their number is m. So these m number of bits are getting into the bit splitter, and we are dividing these m bits into g different groups, and in each group we have p number of bits, and these p bits are divided as p1 and p2 in each different g of the groups. So the p1 is the SNM mapper, which I will talk about it in the following slides, and p2 is responsible of the m area modulation. So after doing the splition and doing the modulation according to the SNM mapper, we are sending those bits into the secondary subblock creator, and we are doing the same thing for all different groups that we have created. And after that we do our we send those bits into the OFDM block creator, and after that point we apply the IFFD, cyclic prefix and DAC, and we do the conventional OFDM modulation. At this point what we differently do is adding an artificial interference noise to create an environment that makes sure that the transmitted data for the legitimate receiver is not available for any eavesdropper who tries to reach our data from the outside. So about that, now I will talk about this artificial noise vector. The artificial noise vector is designed specifically for the channel of the user. For each P1 here that we have created for 4 antenna cases as 0, 0, 0, 1, 1, 0 and 1, 1, our active subcarriers are defined as 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0 and 4 1s. So for each of these 4 different cases we create a specific artificial noise vector to make sure that the data that we send can be cancelled with this artificial noise vector. So at the end, while the legitimate receiver gets a pure signal, the eavesdropper gets a broken signal. So let's give it an example for the activation of 4 subcarriers. The mathematical process of the transmission for the legitimate user can be presented as follows. So we have the general formula with the artificial noise vector NT. So we have the XT, which is our transmitted bits, and we are multiplying it with the channel, and at the end we have our Z value, which is our white noise. So if we do this, the NT4 here, as it is defined as this line, we multiply the xt with each member of this NT matrix. So what we have here is xt plus a over h1, because this is the first index of the N4 matrix, and times h1 plus xt plus minus a over h2 times h2 plus xt plus b over h3 times h3 plus xt plus minus b over h4 times h4 dx, which comes from the integral, plus the zt, which is our noise. So eventually these h values for h1, h2, h3 and h4 are cancelling each other, and what we are coming up with is our pure transmitted signal for the legitimate receiver. On the other hand, since the eavesdropper will not have the same h values as the legitimate receiver, for the eavesdropper's case, the h values will not have a chance to cancel each other, and eventually the signal will be corrupted for the eavesdropper side. A illustration is shown in the figure 2. On the upper hand side, we have the transmitted data with the lower subcarriers, and on top of that we add the artificial noise, and the channel of the legitimate user is this, and eventually these are cancelling each other, and at the end what we are coming up with the pure received data for the legitimate receiver. But at this point for the eavesdropper we have the transmitted data and we have our additive noise, but as you can see on this side the channel of the eavesdropper does not match with the additive artificial noise, so at the end what we are coming up with is the corrupted version of the received data for the eavesdropper. So regarding to this scheme, you can see our bit error rate performance and throughput performances for the legitimate receiver and the eavesdropper. As you can see in the figure 3, while the bit error rate of the legitimate receiver gets better and better as the power increases, the bit error rate of the eavesdropper does not change and it stays stable at the low level. And similarly for the throughput, as the power increases, the throughput of the legitimate receiver improves, but there's no improvement for the eavesdropper in terms of the throughput. So to sum up, we have developed a promising scheme for the future wireless system that requires high security aside the high bit error rate and high spectral efficiency. Thank you for your time.